My name is Jeremy Smith. I'm a senior hardware design engineer, and I've been blogging with Max and his band of reprobates on Programmable Planet about FPGA development and the Xilinx Zinc SoC in particular. So here we have a Zinc Z development board, which has got the Xilinx Zinc SoC over there, which contains dual core A9 32-bit ARM processor with 106,000 logic slices of Series 7 FPGA, which contains fairly standard FPGA features such as half a meg of block RAM, 220 48-bit hardware multipliers, and serial shift registers, and etc. and so on. On this board we also have a 512 kbytes of R3 SD RAM, OLED display, equal flashing lights, which of course are legal requirements on embedded systems designs. We have Ethernet connector, we have a VGA interface, we have HDMI interface, have a analog interface because the Zinc SoC also has two 1 megabit ADCs and multiplexer. So basically I've been in my main interest, apart from the fact that I develop FPGA applications for work, is I've been interested in blogging about the idea that there are a lot of algorithms which are fairly typically implemented in software, which are quite inefficient when implemented in software, and converting the software algorithm into hardware allows us to implement those in a much more efficient manner, allowing us to use the inherent parallelism of the FPGA to execute the algorithm and effectively unroll the software loops, which are often the main stumbling block. And you can think of many examples of the type of software algorithm which benefits from being converted from software into hardware, such as things like video processing algorithms, cryptographic algorithms. You'll find on the APP website a blog which I wrote about implementing DES crypto algorithm in hardware. DES in particular was designed to be implemented in hardware, although a lot of the current implementations are done in software. It's particularly difficult and tricky to implement in software. So one of the features of the Zinc SoC is it does have the dual A9 32-bit ARM processors, and this allows you to integrate your hardware, your programmable hardware, which is doing, if you like, the heavy lifting of the algorithm, with a processor which is really just running housekeeping tasks and reading the results of the hardware processing, if you like. An example of the type of application which benefits from being converted from software into hardware, as I've been discussing on the APP website, is the Game of Life. You may remember the Game of Life, which was written by John Conway in the 70s as a simulation of cellular automata, which looks remarkably like this. If I can show you, here we go. So this is a software simulation of the Game of Life, basically running, and in this case it's running on in Ubuntu, which is actually running on the ARM processors in the Zinc SoC. Now, as you can imagine, we got quite software between the game of life itself and the output, which, as we'll see in a minute, means it's quite slow. So you may remember the game of life is essentially you have an array of memory elements. Each memory element is essentially a software model of a cellular automata state machine, and each state machine has a starting position and a set of rules which it follows, and the software reads the state of each of the cellular automatas and updates their state for the next generation. There are several hundred known rules for the cellular automata to follow, and the behaviour changes accordingly. So in this particular software example, we have an array of a few hundred cellular automata, and we have a starting condition, and because the simulation is being run in software, the processor, every processor, as you know, is essentially serial in nature, reads the state of each individual cellular automata, updates its state, and so there's a constant cycle of reading and writing the RAM containing the state of the cellular automata. The whole collection of cellular automata is called the universe in the game of life. So here we can see the universe is about 100 cells square, and we have this initial starting state. This is the state vector, if you like, of the universe. And as we can see, if I set it running, it will update, and the software goes through a series of steps to generate each new generation of the cellular automata and the game of life as it runs. Now, what's interesting about this is because it's actually running in software and it's running in Ubuntu, it's got so many layers of software it has to go through that each cycle, each generation of the simulation is taking approximately a second to update, and the processor on the SoC is running at full blast to actually maintain this rate of update. So you can imagine that if you've got some embedded system and you have an algorithm, doesn't have to be a game of life, any type of algorithm which can benefit from being updated into hardware, and you have huge amounts of software, it causes all kinds of problems. So what I have done in this, part of my interest is that I have implemented in the SoC device, in the programmable fabric of the SoC device, a hardware model of the cellular automata. Each single cellular automata takes 4 logic slices, and each individual cellular automata has a maximum clock rate of around about 250 megahertz. So that effectively means that in the hardware you can combine the cellular automata into an array very much in the same way as the software simulation. The major difference being, of course, that when we come to update each generation of the hardware model of the game of life, each cellular automata is updated simultaneously because of the fact that the FPGA can access and update each cell on an individual basis simultaneously. We're using the inherent parallelism of the FPGA to do that. So, while I've been talking to you, the software simulation running in Ubuntu has run through, where are we now? We're coming up to 800 generations. The hardware model, which is running in the FPGA, has a limit. It stops at 1,000 generations, and I'd like to show you the output of that. Unfortunately, it stopped it stopped about a microsecond after the FPGA started up, because that's how long it took to go through 1,000 generations. Each generation is being regenerated at 100 megahertz, so every second we go through 100 million generations of the 100 by 100 array of cellular automata. Now you can imagine that that might be quite expensive in terms of hardware. Well, in fact, the 100 by 100 array cell of cellular automata takes approximately 40,000 slices of logic. So we have plenty of logic left for the processor resources. So in this application, the processor is actually communicating with the hardware cellular automata via an ARM Amber bus, and the hardware is configured such that the processor can read a FIFO, which reads the data, it reads the state vector of the game through this FIFO, and under Ubuntu it's treated as a named port. So for example, it's treated as a named pipe, I should say. So if for example I switch to if it comes up, it's not going to come up. There we go. Where are we? Come on, stupid machine. There we go. We can see the terminal here, and I can set it up to read the FIFO and get the results. So here we go. Now we can see that it's reading results from the FIFO. The software running under Ubuntu is treating the FIFO as a named pipe, so you can do things like a cat under Unix, for example, to read the results. Obviously, in a type application, you might have software feeding data into the hardware processor, and the processor doing its thing and then sending the data back out of another FIFO, all of which is read via the Amber bus. Now we can see via the mandatory flashing lights the state of the read FIFO as the software is reading the FIFO, and we can see it's going slightly crackers here because the processor is trying to read all of the data from the state vector of the game live through the FIFO, and the LED shows the state of the fallen empty flags on the FIFO. I've even got a green flashing light. I mean, you can't get much better than flashing lights, I always say. So there you go. It's just a quick demonstration, really, of how you can quite simply convert your software application into a hardware implementation, and you end up with a far more efficient and cost-effective implementation. So I was going to be going to Design West to give a presentation and talk about this, but unfortunately other requirements mean that I have to be elsewhere at the time. So my colleague on APP, Adam Taylor, is going to be giving my presentation, and I'm sure he will be excellent at it, and he will be able to elaborate further on the general principles involved in this whole sort of development cycle. So that's it. I shall catch up with you later, and that's it. Right, bye.